So hello everybody. We will now we will go to part two of chapter three, where we try to find status-based representation of different systems in the time domain. Status-based representation, it means we are working in the time domain. So now we will go to example 3.3, where we try to find the status-based representation of translational mechanical system. We did this solution, this example, in fact. We did this example in chapter 2, but we will repeat it here one more time. But in chapter 2, we got motion equations, and from those motion equations, we found the transfer function. The problem of transfer function is that it can represent single input, single output systems. But when you have multi-input, multi-output, it will be impossible to do this with the transfer function, and it's important to work with status-based representation. So now here we will start with this mass spring number. And from chapter 2, when you try to, we will use here superposition because we need to get the motion equation. And in this superposition, we need to hold M2, move M1 to the right-hand side, right? But first, if you look into the system here, we have two masses, M1 and M2, and they are connected to a wall by a number D, and the M2 and the M1 is connected to each other by a spring, which has a coefficient K, and we will apply a force on M2, try to move it to the right-hand side, and we will try, we have two states here, in fact, we have X1 and X2, and the X1 is a displacement of M1, and the X2 is a displacement of M2. So we call this system MSD, which is mass spring damper system, mass spring damper system. We assume that M1 and M2 frictionless will generate any friction, but of course M1 also it will generate a force to resist the motion, and this force will be proportional to the acceleration of M1. M2 also it will generate a force to resist this motion, and this force will be proportional to the acceleration of M2, which is x2 double dot, right? So we can say here that the spring will generate a force proportional to the displacement, right? D will generate a force proportional to the speed, and M1 and M2 it will generate a force which is proportional to the acceleration. So first we need to find the transfer function x of s divided by f of s for the system. We need to find, we can start with a simple system, in fact, but we did that, in fact, in chapter 2. So we can start with this system for simplicity. And we need to draw the free body diagram, right? Free body diagram, and try to find forces acting on the system. Right, so in this case, we try to begin the solution by drawing the free body diagram. Place on the mass all forces felt by the mass. We assume that the mass is traveling to the right-hand side, thus only the applied force points to the right. All other forces impede the motion and act to oppose it. Spring damper will generate force, and the force due to acceleration point to the left. It will I mean the spring, the damper, and the mass, it will generate a force which will try to work on the opposite direction, right? So now we need to draw the free body diagram first. So we will draw this M, right? Draw M, right? This free body diagram, and try to plot forces which are acting, right? So we know that F of t is a force acting on M to try to pull it to the right-hand side. And when you do this, there will be forces which will be generated from the spring, for example. And this force, it will be K multiplied by X of t. It will generate a force proportional to the displacement. As a damper, it will generate a force proportional to the speed. So it will be FV multiplied by dx by dt, which is the speed. And the M, it will generate a force which will act on the other side as well. And this force will be proportional to the acceleration. So it will be M d square x by dt squared. So just to try to put it in S domain. So replace x of t by x of s, f of t by f of s, and k multiplied by x of t, it will be k multiplied by x of s. FV, I mean dx of t, it will be sx of s. So when you transfer when you apply Laplace transform, and this one also it will be m s square x of s. So it will be like this one. So sum of powers on the left equal to at equilibrium, sum of forces on the left equal to powers acting on the right. So it will be starting from the bottom to up. So we avoid ordering it one more time. So it will be, and take x of s as a common factor. So it will be ms square plus fvs plus k multiplied by x of s equal f of s. If you want to get the transfer function, so transfer function will be the output, which is x of s divided by f of s. So it will be 1 divided by ms square plus fvs plus k. So this is my system, and you can put it in a block diagram similar to this one, where the input is f of s, and the output will be the displacement. So this device, it's very similar to the devices which you use in the gym, for example. So maybe there is a system, you try to apply a force, you try to pull it to one side to make some displacement, right? So we apply force on the side to change x of t. So the transfer function will be like this one. So finally we got it, but here it's more details. So finally we got the system representation, and it's a transfer function. And as you can see here, it's a single input. They call it SI, single input, single output, seesaw. Right, this one, single input, single output. So it's single input, single output. And of course, here we assume that all initial conditions equal 0. So we assume that x of 0 was 0, correct? So the system was standstill before modeling it. So we assume 0 initial condition when we try to get the transfer function. So if you want to do this in a state space representation, you need to start from the differential equation, right? So here, if you look into the steps, we got first, this one, when it was in time domain, we got this one. This one we call it differential equation, right? This is my differential equation, which describes the system. And after getting this differential equation, we apply Laplace transform. So we convert it into that format. And from that format, we will be able to get the transfer function. But if you want to get state space representation, so in fact, we can start from the differential equation. This one, it's the motion equation. It's differential equation, and it's second order because we have here d square x by dt square. So if you can just want to write it in a nice way, you can put it in this way. It will be mx double dot, right? So you can put it in that format. So it will be mx double dot plus cx dot of fv. I just try to make it simple, so I will call this one c, right? Plus kx. So just remember that fv is replaced here by c, just to make it easy for writing. So now we can have our differential equation will be like this one. If you want to get a state space representation of this differential equation, we need to choose state variables. So we will choose the first state variable, which is x1 equal x, displacement. So we choose x1 equal x, and we will differentiate this one. So x1 dot will be x dot, right? It will be x dot. We will call it x2. So if x1 is distance, x1 dot, which is the first derivative of the distance, or rate of a change of distance, it should be speed. So in this case, we will just differentiate this equation. So it will be x1 dot equal x dot. We will call it x2, right? So in this case, in fact, we can say that x1 dot equal x2. So this one will be my first state equation, x1 dot equal x2. We will differentiate this equation one more time. So in this case, x2 dot equal x double dot. Just differentiate that part. So x2 dot equal x double dot. And in fact, x2 was the speed. So x2 dot, it will be acceleration. So x2 dot equal x double dot. And we will substitute into this equation to get x double dot. So from this equation, x double dot equal minus c divided by m x dot, right? So I just take that part to the other side by negative and divide by m minus k divided by m multiplied by x plus 1 divided by m multiplied by f, which is applied force input. So in this equation, what is x dot? From this equation here, x dot is x2. So this one will be minus c divided by m multiplied by x2 minus k divided by m multiplied by x. What is x? From this equation, x is x1 plus 1 divided by m multiplied by f, which is the input. I will call it u. So as you can see here, x2 dot equal, just correct, arrange it. So it will be minus k divided by m multiplied by x1 minus c divided by m multiplied by x2 plus 1 divided by m multiplied by u. So this one will be my second state equation. So now we have two state equation, x1 dot equal x2, you see, and x2 dot equal that part. And just remember, the state equation is x dot equal ax plus pu, and the output equation y equals cx plus du. So now, in fact, my second order differential equation is composed into, or we break it down into two first order differential equations. The first one is x1 dot equal x2, and the second equation, it will be x2 dot equal this one. So we will just put it in matrix notation. So x1 dot is the first row. The first equation, we will write it in the first row, x1 dot equal x2. x1 dot equal x2. So this, it will be 0 and 1, right? Because 0 times x1 it's 0, plus 1 times x2 it's x2. Plus 0 because we want plus 0 times u. We will go to the second equation, x2 dot equal the coefficient of x1, which is minus k divided by m, minus c divided by m multiplied by x2, plus 1 divided by m u. So this one will be my state equation. This is very important. This state equation, it's the fingerprint of your system. Now, you need to select the output equation. Of course, in our system here, we try to apply force because we need to control the displacement. So, for example, if you want to change x of t from 0 to 1 centimeters or 1 meter, how much force we need to apply here, right? So, in fact, my controlled variable here will be x of t. So the output will be x of t. So y equal x. What is x? Yeah, from this here, from the definition of when we choose our states, x equal x1. So y equal x equal x1. So in matrix notation or in vector notation, it will be 1 multiplied by x1 plus 0 multiplied by x2. So it will be like this one. Of course, if you want to add the other part, it will be d multiplied by u, but d here it will be 0. So this one will be my output equation. So now we have the state equation and the output equation of your MSD system, right? MSD system, mass spring number. So now, if we want to compare, this is your system. This is your status based representation, G of S. I will write it here one more time. So G of S equal 1 divided by MS squared plus FVS plus K. So this is my status based representation of your system. Just remember here, we don't have C. This one is FV. And the status based representation and the output equation will be like this one. So in fact, you can have your system in a status-based representation, and you can have your system as state equation and output equation. This one, it's in the time domain. This one, it is in the frequency domain. This one, the system must be single input, single output. My system here, it could be single input, multi-output. It could be multi-input, single output, multi-input, multi-output. So we don't have those limitations which are opposed by working in frequency domain with transfer function. So now we need to go back to example 3.3 and try to solve it. We will apply here superposition because we have 2 degrees of freedom. Remember, in fact, here we have two variables we need to control. We need to control x1, we need to control x2. So we have 2 degrees of freedom here because we have M1 and M2. We can move M1, hold M2, move M2 and hold M1. So here, in fact, we will use superposition to get the equation of motion, and we have 2 states, x1 and x2. Remember, right? So we need to write the motion equation of equation of motion, and after that, from this one, we will be able to develop our transfer function or state space representation. So we will start with the first degree. So in this case, we will hold M2, right? Hold M2 and move M1 to the right. So we will move this one here to the right. When we move it to the right, what will happen? What will happen? In fact, this number, it will generate a force which will be proportional to the speed of M1. So it will be dx1 dot. So I would like to call this one dx1 dot. It will generate a force opposing M1. And this force equal dx1 dot. M1, it will, the mass, it will generate a force proportional to the acceleration. So it will be M1 multiplied by x1 double dot. Just make it easy instead of using dx by dt or d square x by dt. So it will be M1 x1 double dot. And if you move M1 to the right, in fact, you have a spring here with coefficient x, k. This one also, it will try to resist this motion to the right-hand side. So it will work on the left-hand side, and it will generate a force equal k times x1. Right? So this is the first part. After that, we will hold M1, and we will move M2 to the right. When we do this, what will happen? When you hold M1 and move M2 to the right, in fact, this spring, it will try to pull M1 to the right as well. So it will generate a force to drag M1 to the right. So this force will be K multiplied by X2, because M1, we hold M1. So in fact, X1 is 0. So this one, it will generate a force called Kx2. Now we will combine those forces. We will sum it together in the right direction. So as you can see here from this figure, we have 3 forces acting to the right. We will add it here. So it will be Kx1. This one, it will be dx1 dot. This one, it will be M1 x1 double dot. And we will have only Kx2 working to the left, to the right-hand side. So we need to write this equation at equilibrium. The forces acting on the left equal to forces acting to the right. So just to sum it, so it will be M1 x1 double dot. So it will be M1 x1 double dot plus dx1 dot plus kx1 equal kx2. Just to try to move kx2 from the side to the other side, because we have coefficient k. So it will be k multiplied by x1 minus x2 equals 0. So this one will be equation number 1. This one will be equation number 1. We will go to the second part. We need to do the same for M2. So we will do the same for M2. So it's the same. We will hold M1, right? In this case, and move M2 to the right. And we will see forces acting on it. When we try to move M2 to the right, what will happen? So we have F, because F here is acting to the left, to the right. So this one will have F, because this is the input. But K will generate a force to oppose this motion. It will generate a force acting to the left. So it will generate a force equal K times X2. It will be Kx2. M2, the weight, the mass, it will generate a force proportional to the acceleration of M2. So it will generate a force called M2 x2 double dot. So it will generate a force equal to M2 x2 double dot. So this is the first step. The second step, what will happen? We will hold M2 and we will move M1 to the right. When we do this, M2, it will push X. It will push the spring, right? When we're moving M1 to the right, M1, it will push the spring to the right. So in fact, it will generate a force which will try to push M2 to the right. So it will generate a force which will push M2 to the right. This force will be proportional to the displacement of x1, right? So it will be kx1. It will be kx1. Now we will do summation, summing all forces. So we will have here this one, sorry, it's M2. So we will have F acting to the right. We will have also Kx1 acting to the right. And on the other side, we will have Kx2. And we will have M2. We'll call it, write it more time here, M2 x2 double dot. So write the equation at equilibrium. sum of forces acting to the left equal forces acting on the right. So it will be M2 x2 double dot, it will be M2 x2 double dot plus K of x2 minus x1, right? We will just take this one to the other side. So it will be K multiplied by x2 minus x1 because we will move this one to the other side. So we need to multiply it by negative to ensure that it's still acting on the right, equal F. So this one will be equation number 2. So now we have two equations which are representing, because we have 2 degrees of freedom, in fact, right? We have two equations, two differential equations. So we have equation 1 and equation 2. If you want to get the transfer function, so we will convert it into S domain if we want to get the transfer function. So in this case, we will apply Laplace transform. So apply Laplace transform to equation 1. So it will be M1 S square x1 of S plus ds x1 of S plus K multiplied by x1 of S minus K multiplied by x2 of S equals 0. Apply Laplace transform to the second equation. So the second equation, it will be okay. Okay. We are still here in the first equation, right? So we are still in this first equation. So try to make it simple. So we will have x1 of S in one side, and the x2 it will be on the other side, right? We will take this one to the other side. Take x1 as a common factor. So it will be m1 S square plus ds plus K multiplied by x1 of S equal K x2 of S. If you want to get maybe a transfer function here, which x2 divided by x1, we can get it. So x2 divided by x1, it will be that part divided by the coefficient of x2, which is K. So it will be this. So we have the first part. We will go to the second equation, apply a Laplace transform. So it will be m2 s square, m2 s square, x2 of S plus K x2 of S minus K x1 of S equal F of S, right? So we will get x2 of S in one side. We will take this one to the other side, divide both sides by x1 of S, because we have here x2 divided by x1. I mean, we have this value, so divide both sides by x1 of S. So we will have here x2 divided by x1 equal F divided by x1, because in reality we need to get G of S, which is x1 of S divided by F of S. We need to get this one. So we need to get x1 of S divided by F of S, or F of S divided by x1 of S in one side. So here divide by both sides by x1 of S, so we will get this one in one side. So it will be like this one. So it will be that part multiplied by that part minus K, right? So in case, just substitute this value here, right? And just do this multiplication and get your transfer function. So at the end, after analysis, doing those steps, we will get this transfer function at the end. So we will get this one at the end. This one will be my transfer function. And just remember, this is a transfer function for a single input, single output. If we need to draw the block diagram of my system, when the input is F of S, we want to control x1 of S. Because we've got this transfer function, I will call it G of S. But if you changed your mind, and if you want to control, instead of controlling x1 of S, and I need now to control x2 of S, what will happen? I need to do those derivations one more time, because now the transfer function, this transfer function will not work with me here. I need to get a new transfer function, right? Because I can have only one transfer function describing relationship between input and output. So if you change your mind and you want to get x2 instead of x1, no, now it's different. Now you need to go back to those steps and try to solve for x2 this time, right? You need to solve for x2. But of course, in status space representation, it's much simpler, because the most important is to get my status space representation. And once I have my status space representation, I can write any output equation. If I want to control x1, it's okay. I will write an output equation for it to get to read it. If I want to get x2, it's okay. I will just change the output equation. So it will be easy. So the most important in status space representation is to get the state equation. And for the output equation, you can change it at any point without any problem. So now we need to write the status space representation of my system. So we will start from the two differential equations. Remember, we got those two differential equations. So we will start by selecting the state variables. So we have x1 and x2. So I will make it here in a much simpler way instead of using v1 and something. So I will start with x1, my first state. Yeah, because here, yes, we need to give it different names because we already have x1 and x2. So we cannot select x1 and x2 one more time, right? But okay, I will call it x. So we will call it x1 and v1, right? So we will start with so I will just start with like something like this one. X1 equal x1, which is a displacement of the first element m1. So differentiate this one, so it will be x1 dot equal x1 dot. We will call it v1, right? We will call it v1 because this is the speed, right? We will differentiate this one, so v1 dot equal x1 double dot, right? It will be x1 double dot. x1 double dot from equation 1. We will get here equation 1. I need to get x1 double dot. So x1 double dot, it will be minus k divided by m multiplied by x1, because this is one of my states, plus, yes, plus k divided by m multiplied by x2, that part, right? Minus d divided by m1 multiplied by x1 dot. What is x1 dot? It's v1. So this one will be my equation. We will go to the second equation. I need to select another state. So I will call it x2 dot x2, or x2 equal x2, x2 dot equal x2 dot, which is v2, v2 dot equal v2, v2 dot equal x2 double dot. We will substitute it from the equation. So it will be, and we will take the part to the other side. It will be plus k divided by m2. So it will be k divided by m2 multiplied by x1, right? x1, which is my first state, minus k divided by m2 multiplied by x2 plus 1 divided by m2 multiplied by m. So just to make use those equations to write those state equations. So in fact, this equation is second order. This one, this second order, it will be decomposed into two first order. This one I will call it 1, and v1 dot, it will be this one 2. So in fact, equation 1, it will be decomposed into 1 and 2, 1 dash and 2 dash, for example. And equation number 2, it will be decomposed into this equation. I will call it 3 dash and 4 dash. So stated space representation, it's converting the differential equation into a set of first order differential equation. Because the system differential equations are two second order equations, we will decompose it into 4 first order differential equation. Now we will write it in a status space in form, in matrix notation. So my states will be like this one. It will be x1 dot, do you see x1 dot, v1 dot, v1 dot, and x2 dot, and the v2. It will be like this one. 4 states. So it will be very large matrix multiplied by my states, which is x1, v1, x2, v2, right? Plus something multiplied by input. So we will look into the first equation, x1 dot equal v1, right? x1 dot, so this one will be 0, 1, 0, 0. And also this one will be 0. We will go to equation number 2. So it will be minus k divided by m, minus k divided by m. The second part, it will be minus d divided by m. Yeah, it's called m1. Yes, m1, sorry. So it will be minus d divided by m1. And the x2, it will be k divided by n1, 0. And we don't have any inputs, 0. The third equation, x2 dot equal v2. So it will be v2, it will be 0, 0, 0, 1. force equation, it will be K divided by M1, K divided by M2, sorry, minus K divided by M2, and after that 0. Yeah, sorry, this one 0, this one minus K divided by M2, this one will be 0, just put it in the order, this one 1 divided by M2, we have here 0. So this one will be the this one will be the matrix in state equation. So this in we call it state equation. State equation. This one, this is the most important. This is a fingerprint of your. Oops, that we did it correctly. Yes. So this is the state equation which will describe your system. So your system has 4 states. Those 4 states are x1, v1, x2, and v2. So in fact, it's the displacement of your m1, speed of m1, displacement of m2, and the speed of speed of m2. So what about the output equation? It's up to you. So do you like to control what? Do you like to control the speed of x1? So in this case, y will be x1. Do you like to control the speed of m1? So y will be v1. Do you want to control the displacement of m2? So y will be x2. If you want to control the speed of m2, so y in this case will be v2, right? So if it is this one, so it will be 1, 0, 0, 0, multiplied by my states, x1, v1, x2, v2. If you want to control v1, so this equation, it will be 0, 1, 0, 0, multiplied by this states. If you want to control x2, so this one will be 0, 0, 1, 0, multiplied by x. If you want to control v2, so it will be 0, 0, 0, 1, multiplied by x. So it's up to you, right? So the most important here is to have state space representation. And once we have state space representation, we can decide which state we want to control, right? If you want to control x1, write an output equation to help you to get access to x1 by reading it. If you want to control v1, write an equation to get access to v1. If you want to control x2, v2, and so on. So now we have a skill assessment exercise. It's a more complex system, and this system has 3 degrees of freedom, right? It's just the same, but it's just more degrees of freedom. So we need to use superposition, which will be a little bit more complex. And you have here, we have x1, we have x2, we have x3. And you have the force acting on M1. So this one will be M1, and the force acting here in M1. So we have M1, M2, M3. So the idea here, if you want to control X3, how much force should we apply on M1? So this is the idea of control system. So we need to build a model, state space representation of your system. And after that, we will design a controller which will calculate how much force we need to apply in M1. For example, to calculate the displacement of M3, which is x3, or speed of M3, which will be v3. So in this case, in fact, we will have 6 states. So should expect is that we will have, my states will be like this one, it will be x1, v1, x2, v2, x3, v3. So it will be this one. So the matrix will be very complex because we have, it will be 6 times 6. So we can go through it very quickly. So we will start by moving M1, hold M1. Sorry, move M1 to the right, and hold both M2 and M3, and define the forces which are acting on M1, and write those equations and repeat this process as we did in this example. So just to go through the solution here, so we can go quickly. If you will hold M2 and M3, so move M1 to the right and hold M2. Of course, when we hold M2, mistake, we will not impact it because we are holding M2 in the middle. So, and try to move M1 to the right hand side. So what will happen here? So in fact, the spring, it will generate force which will reject this movement. It will act on the opposite direction. So this force, it will be K1 multiplied by X1. So it will be 1 because k here equal 1. So in fact, it will be 1 times x1. So this one will be x1, the spring. We will have here m1, it will generate a force accelerating proportional to the acceleration of m1. So it will be m1, which is 1 kilo multiplied by x1 double dot. So this one, in fact, this one will be just x1. This one will be x1 double dot, right? We have the force acting to the left, and also this number, it will generate a force proportional to the speed of m1. So it will be c multiplied by v1, or you can say c here equal 1, in fact, so it will be just x1. We will move m2 to the right and hold m1. In this case, this number, it will generate a force which is proportional to the speed of m2, because m2 is moving, and this force will try to drag m1 to the right, so it will generate a force equal also x2 dot. So this force will be x2 dot. Sum all those forces and write an equation. So when you do this, you will get this equation, which is equation 1. After doing this, you will repeat it with m2. But in case of m2, we need first to maybe hold m1 and m3 and move m2 to the right-hand side, right? When we do this, what will happen? We will get this. We will find that this number, it will generate a force proportional to x2 to oppose this movement to the right. Weight of m2, it will generate a force proportional to the acceleration. And also this number, it will generate a force which is acting on the opposite direction because it will resist the movement to the right. So it will generate this one. So this is the first step. And after that, we will hold m2, move m1 to the right. When we move m1 to the right, this one will generate a force which will try to force m2 to the right. So it will generate a force equal c1 multiplied by x1 dot, right? And we will do the same with m3. So we will hold m2 and we will move m3 to the right. When we do this, k2 will generate a force, try to drag m2 to the right. So this force will be k2 multiplied by x3, right? Summing those forces and write the equation of motion. So we will get the second equation of motion. So it will be this equation, right? We will do the same for m3. In case of m3, we will hold m2 because it's not connected anyway with m1. So just hold m2 and move m3 to the right. What will happen? When you try to move m3 to the right, this one will generate a force opposing. This force will be k2 multiplied by x3. m3 will generate a force proportional to the acceleration of m3. So it will be m3 multiplied by x3 dot. And also this number, it will generate a force to the opposite direction because it will oppose this movement to the right. So it will generate a force called C2 multiplied by x3 dot. This one, it will be C2 multiplied by x3 dot. After that, we will hold m3 and we will move m2 to the right. When this happens, this spring will try to push m3 to the right. So this force will be k2 multiplied by x2. Just to make it easy for you, sum all those powers, write the equation, but it will be easy. All those variables equal 1. So k1 equal 1, m1 equal 1, m2 equal 1. So when you substitute all those coefficients by 1, the three equations will be much simpler. So you will get those three equations. Try to write it in matrix notation and substitute those values, and try to take inverse Laplace transform to have it in time domain. So we will have those three equations: equation 1, equation 2, equation 3. Apply inverse Laplace transform to have the differential equation. So it will be x1 double dot and order it. So it will be x1 double dot equals this, x2 double dot equals this, x3 double dot equals this one. Try to define your states. So I can select the first state. So I can say that, okay, my first state, it will be z1 equal x1. Differentiate. So x1 dot equal x1 dot equal x2, right? In fact, Z1 dot equal X2 will be my first state equation. Differentiate this one. So X1, Z1 dot equal X1 dot equal X2. Differentiate this one. So Z1 dot equal X2, X1 double dot, sorry, X1 double dot. We will substitute this value from this equation to get details. So it will be like Z1 dot equal Z2, Z2 dot equal X1 double dot. It will be that part. Substitute those values. Z, so we select Z1 equal X1. Differentiate this one. So Z1 dot equal X1 dot equal X2. Sorry, equal Z2, not equal Z2. Differentiate this equation, so Z2 dot equal X1 double dot from equation 1, X1 double dot equal minus X1 dot. This minus X1 dot, it's minus X1 first. I will start with this minus X1. What is X1? It's Z1, right? So it will be minus Z1 minus X1 dot, it's Z2, so it will be minus Z2 plus X2 dot. What is X2 dot? X2 dot, in fact, it's Z4, right? So it will be Z4, right? Z4 plus F, and so on. So in this case, we will get those equation Z1 dot in one side, and the states on the other side. We will write it in matrix notation, so it will be Z dot equal A multiplied by Z plus P multiplied by U. So it will be like this one. So we can get, so as you can see here, this one is 6 times 6. And we have six states. So the state vector is 6 times 1, right? So to convert the transfer function into a state space representation, one advantage of a state space representation is that it can be used for simulation of physical systems on the digital computers. We can work on time domain, just a very simple for loop, and we can simulate any system in time domain. Convert the transfer function into differential equation by cross multiplying and using inverse Laplace transform if you want. So if you have a transfer function like g of s, which is the output y of s divided by input, which is u of s, you just need, and it's equal something, you just need to do cross multiply and get y of s. And after that, apply inverse Laplace transform to build the differential equation, the solution, which is y of t. Choose a set of state variables called phase variables, where each subsequent state is defined as the derivative of the previous state variable. And it's easy. So now we can take another example. And in this example, we have a transfer function with constant. In fact, we solved this one before in the last chapter, but it's very similar because we're just repeating ourselves. We have this transfer function, and we need to find the differential equation, right? So we have a transfer function. The transfer function equals C of S divided by R of S. So your system looks like this one. The system to your system is R of S, and the output is C of S. We have here the transfer function Z of S. We need to get the differential equation. Once we have the differential equation, from the differential equation, we can write state space representation. So just to do cross multiply, so it will be C of S multiplied by that part equal 24 multiplied by R of S. Take inverse Laplace transform. So S cubed multiplied by C of S, it would be C triple dot plus 9C squared C of S, it would be 9C double dot plus 26S C of S, it would be 26C dot plus 24C, it would be 24C equal 24R. So this is my differential equation, right? If we want to write, and of course we're assuming zero initial conditions. So if you want to, now I want to write state space representation of this system. So I can just assume my states. We need to give names to my states. So I will say that, okay, my first state x1 equals c. Differentiate. So x1 dot equal c dot equal x2. Differentiate this one. So x2 dot equal c double dot equal x3. x3 dot equal c double dot triple dot c triple dot. We can get it from this equation. So it will be minus 24c minus 26 c dot minus 9 c double dot plus 24r. Just substitute the states. What c in fact is x1, so it would be minus 24 x1 minus 26 c dot. What is c dot? It's x2 minus 9 c double dot. C double dot is x3, so it will be x3 plus 24r, which is the input. I will call it c. Now I need to write it in matrix notation. So it will be like this one, x1 dot x2 dot x3 dot equal x1, x2, x3 plus this one. So the first state equation x1 dot equal x2, x1 dot equal x2, so it will be 0, 1, 0. This one will be 0. The second equation x2 dot equal x3, so it will be 0, 0, 1. This one also will be 0. The third first order equation, it will be 24x1. So this one will be 24 minus 26 minus 9 plus 24. So it will be like this one. So this is my state equation. Yes. We have something called block diagram showing those phase variable. In fact, we can draw this graph from the state equations, right? So we are starting from the highest, from x3 dot, right? We need to start from x3 dot. I mean, we have those three equations. We got this x3 dot equal this number, right? So just focus on equation number 3, right? Equation number 3. So if you want to draw this graph, you need to just start with a summing point, and the output from this summing point will be x3 dot. And I will get the equation of x3 dot. Yeah. So x3 dot equal x3 dot equal 24x1, right? 24. Yeah, sorry, minus 24. Minus 24. It's minus 24x1. Okay. Okay. Yes, minus 24x1. So I have something, yes. Minus 24. So minus 26 x2 minus 9 x3 plus 24r. So this is the third equation, in fact. So if you want to draw this graph, in fact, just start with a summing point, write x3, integrate x3 to get x2, integrate x3 dot to get x3, and integrate x3 to get x2, and integrate again x2 to get x1, right? When you integrate, you will get x1. So the output here will be like maybe x1, assuming the output is x1. And we will look into this equation. What is x3? x3 is minus 24x1. So it will be minus 24. It will be like this one. Minus 24x1. Minus 26x. So multiply by 26 minus. And for x3, it's a minus 9. So it will be 9. This one, it's negative. And the 24r. So we need to have here 24 multiplied by. So, I mean, plotting it, it's easy. In fact, you start by the third state equation and just start with a summing point. The output from the summing point would be x3 dot, and then integrate x3 dot to get x3, integrate x3 to get x2, integrate x2 to get x1, and just write the equation of x3. So it will be minus, it will be in fact those coefficient in negative. So it will be minus 24 times x1, minus 26 times x2, minus 9 x3 plus 24 multiplied by the input. So this is the graph. So this is the solution in details. So just select the state variables, choose the state variables as successive derivatives. So we assume x1 equals c, x2 equals c dot, x3 equal 3 c double dot. In fact, I like it in this way. I can just say, okay, x1 equals c, differentiate, so x1 dot equal c dot equal, I will call it x2, differentiate this equation, so x2 dot equals 3 double dot, and I will call this one x3, differentiate x3, so x3 dot will be c triple dot, right? 3 triple dot, we will go to the differential equation and find the what is c triple dot, so it will be minus 24 c minus 26 c dot minus c minus 9c triple dot plus 24r, substitute values, so it will be minus 24c. What is c? C is x1. What is c dot is x2 minus 26 x2 minus 9c double dot. C double dot is x3 plus 24r. So now we can get this three equation. So x1 dot equal x2 will be the first equation. This one will be the second equation. This one will be the third equation. So those are the equation which we are getting here. We will write it in matrix 4. So we will get this equation. And for the output, it's up to you to select, right? Maybe someone he will say, okay, I need to control C. So in this case, if y equals C, we will look into what is C. C is x1. So in this case, it will be x1. In matrix notation, so this one will be 1, 0, 0, multiplied by state vector, which x1, x2, x3. So just you need to practice. If you want to convert, I need to check time, how much time we are using now. I guess we should stop here now because we are taking more time. We will stop here and we will go back to, we are at slide number 14. We still have only 10 slides in chapter 2, but we will leave that part for part 3 of chapter 3. So things are not too long. So thank you very much for following, and we will meet again in part 3 of chapter 3, where we will try to convert a transfer function with a polynomial in the numerator and solve example 3.5.